The branch of science that deals with the relations between heat and other forms of energy is called thermodynamics. The main ideas regarding this topic are heat and thermal energy, enthalpy and entropy, and the laws of thermodynamics. Heat itself is the transfer of energy from multiple objects. Thermal energy is the energy that is generated from the heat. On the microscale, it is the movement of atoms in the substances. The increase of movement in these particles increases the amount of energy that is given off of that object. An example of this is the immersion heater lab we did in class. Electricity ran through the immersion heater's wires, creating energy, and this energy was transferred into the water, heating it up. The water molecules started to move and vibrate faster, which in turn increased the temperature. In this unit, we looked at the ways objects' temperatures change when in contact due to thermal equilibrium. The equation of thermal equilibrium is mc delta T equals mc delta T, which allows us to find the temperature of an object or substance when given the 5 other variables. 2 more variables can be introduced. The latent heats of fusion and vaporization are used to display the change in state. All these variables are used to mathematically show why or how 2 systems reach equal temperatures. The labs regarding this unit we've done in class involve thermal equilibrium. As energy from the immersion heater increased while it was in the water, the 2 systems wanted to be at equilibrium with each other, so the temperature of the water increased. During Webb's heater crisis lab, we looked at which fuel burned the best. This refers to thermal equilibrium, as the specific heat capacities of each of the fuels were different and the mass changes could be used to calculate with the equation which was best to use. There are 4 laws of thermodynamics. The first law is the law of conservation of energy. Energy cannot be created nor destroyed, but it can change form. A quick example of this is ice melting, as it possesses the same amount of energy in its solid state and in its liquid state, but it simply changes form. This graph shows that energy entering a system can either break the intermolecular bonds, which is just changing state, or increase the kinetic energy, which is just changing the temperature, but it can never do both at the same time. The second is labeled as the law of entropy. Heat does not flow spontaneously from 2 objects. The disorder of a system is always increasing. This respects the first law, as total energy is conserved but useful energy is decreased, and going back to the ice cube example, the entropy increased in the water as it went from a solid state to a liquid state. The third law states simply that no system can reach absolute zero. Although many have gotten close to 0 Kelvin, due to quantum mechanics there is always motion at the atomic level. The final law, also known as the 0th law, states 2 systems are in thermal equilibrium so long as both are in thermal equilibrium with a third system. During a chemical reaction, energy is either released or absorbed, which is displayed as enthalpy. This may sound similar to heat, but the difference is that enthalpy refers to the bonds breaking or forming during a combustion reaction. The release of heat equals the change of enthalpy. It is displayed as change in H, or delta H, and is simple to discover whether or not a system has absorbed or given off heat. If the calculations show that delta H is positive, that means the reaction is endothermic, whereas if it's negative, the reaction is exothermic. An example would be the combustion of methane. The bonds of hydrogen and the 2 pairs of bonds of oxygen break and reform in different places to form new molecules. It takes energy to break bonds and releases energy when forming bonds. There is a graph that is able to tell whether a reaction will always, sometimes, or never happen. If entropy is positive and enthalpy is negative, the reaction will always happen. If both are positive or both are negative, they will sometimes happen, depending on whether the temperature is high or low, and if entropy is negative and enthalpy is positive, the reaction will never happen.